Let's just get started. So, we were talking about this idea of electric charge, and we sort of hopefully got some semblance of the idea that the interactions between electric charge are like off the scale compared to what we normally worry about or what we think about with gravity. You remember the simple problem that we did with just a couple Coulomb charges, and they were placed a ½ meter apart, and we came up with some number of force of interaction being regular, 10 to several powers, several orders of magnitude. This is crazy stuff. So what I thought we'd do was let's shrink it down and look at a microscopic scale and just get a sense of really how these things look in perspective. So to this end, let's just look at what happens inside a typical atom, and we'll use an atom that just consists of a couple positive charges at its kernel nucleus. So we'll, for genericity, we'll talk about two positive charges, and let's call them Q1 and Q2. And they both have a magnitude of 1 quantum of electric charge. So 1.602 times 10 to the negative 19th coulombs. And they're separated. So now, we all kind of know what the name of these little positive charges in the center of an atom are, right? Protons. But and so the dimensions of an atomic nucleus, just to give you a sense, from chemistry, if you've had any chemistry and you've ever attempted to measure the size of an atom, or maybe even just talked about it in classes, typically on the order of what we call angstroms, which is about 10 to the negative 10th meters, or tenths of billionths of meters. Well, if you look even closer at the nucleus, the order of magnitude is about 10, well, for the whole nucleus, is typically on the order of about 10 to the negative 15, or 5 orders of magnitude smaller than the size of the atom itself, or the span of the electron. So let's use a value of about 5 times 10 to the negative 16th meters, so about a half of 1/10 to the negative 15, if you will. It's about a half of a typical atomic diameter. So we can sort of remind ourselves that we could think of this as some kind of a nucleus, but we just want to look at the charges and assume that they're point charges at just, some relatively close proximity. And well, we can call maybe this one Q1 and this one Q2. And let's just do two things. Let's just calculate the electric force, and then we'll calculate the corresponding gravitational force of attraction between these two point charges. And so maybe to add to this, let's just note that the mass of each of them, the mass of one, which is equal to the mass of two, is about 1.67 times 10 to the negative 27 kilograms. Typical proton mass. Okay. So first of all, let's calculate the electric force on, well, let's just pick one. How about Q2? Evidently, I'm grammatically challenged as usual today. About what is. As a former president would say, depends on what the word is. Separate context. So what is the electric force on Q2? So we'll start by establishing a quick free body diagram for Q2. And, okay, it looks something like that. And if for no other reason, then we can infer, because they both have the same or like charges, the electric force exerted on Q2 is going to be directed toward Q1. So this being said, but because this is the center of our action, I'm going to go ahead and define a coordinate system. Right? Vectors don't mean anything without coordinate systems. So I'm going to go ahead and define a coordinate system that maybe looks something like this. I'm going to call this the x direction and this the y direction. It's a one-dimensional problem, but as soon as it isn't, we'll have to deal with other aspects. We might as well start now. So I'll define my coordinate system, and now we can look at how these things are related. We've got one force. The way we would calculate Fe is we would say that there is a relationship between the interaction of two electric charges that are related to the product of each of their individual charges. And it's inversely related to the square of the distance between them. And some constant, we call Coulomb's constant, about 9 times 10 to the 9th Newton meters squared per Coulomb squared. Very strange number. It's a fudge factor. It's an engineering factor, excuse me. Keep these things together. I even forget if this particular textbook uses it, but I'll tell you, for any type of point charge force problem, it's always easier just to use K rather than the long form of the number, even though it ends up being a little bit less fundamental. And now I better make a side note. I think the textbook also says that we'll just note that this K corresponds to 1 over 4 pi times a different constant that we call the permittivity constant.
Is that for the wavelength or something like that?
No, this is not the wavelength constant, this is not the wave number, this is just the Coulomb constant. And if you want, just to clarify, we did this with Boltzmann's constant last term. Let's just put a C there so we know we're not using an elastic constant or some other darn thing. Just too many letters, and physicists are sloppy enough with their number or with their variables, so you just throw whatever it is, just knowing what it is in that context. And this epsilon naught corresponds to 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. And this is referred to as the permeabilities in vacuum. It actually is different in other materials like insulators, but in a vacuum, it's this ridiculous number. So probably at some point, both of these numbers you ought to have in your calculator stored somewhere. This number is particularly important. We typically focus more on this as we move along, and the reason is that, well, aside from the fact that it holds prominence as one of our fundamental constants in nature, it's one of two quantities you actually need to calculate the speed of light without ever measuring how far light travels. So, I mean, it's that fundamental. And to that end, it was instrumental early on in establishing that light and electromagnetic behavior are in fact one and the same. So but for now, for these problems, it's usually just easier to go with this as a number. Okay, it's just being practical. So now we got another issue. We point in the direction of R. Right? This has a vector quantity. The question is, what direction does it point? Well, it points in the direction from the charge that is disturbing along the line of action to the charge that's being disturbed. So we're looking at what's going on with Q2. So we place our origin at Q1, and our x direction in this particular assignment is, in fact, the direction of that force. So whether it's a positive or a negative quantity, which will be determined by electric charge, I know that I can define it in terms of this I direction. So at this point now, we can calculate some values and put some numbers in, and it's pretty straightforward plug and chub. So we've got about 8.99 times 10 to the negative, or I'm sorry, the positive 9th Newton meters squared per coulomb squared. Multiply this by, since we have the same value of charge, it's 1.602 times 10 to the negative 19th coulomb squared, Q1 times Q2. I'm just not going to write out all of it, but it's both of them. And then I'm going to divide this whole thing by the distance of separation, which is 5 times 10 to the negative 16th meters. And I'm going to have to square that quantity. And again, it's in the I direction. So plug these numbers into the calculator. It's a negative 38, negative 29. It's about a positive 3, maybe 4. So, or 2. So we're looking at the order of hundreds to thousands of newtons. Let me give you a better number. I'm just looking at powers of 10.
22.9.
What's that?
22.9.
Almost 1,000. Wow, so this quantity is about 920, call it 23. I don't have very good digits here anyway, newtons, and this is in the I direction. Well, does this strike you as interesting? Forget about anything else. We're just talking about a simple helium nucleus interaction, if you will. We got two little protons pushing against each other in the nucleus. They have to be repelling because they have the same charge. And the amount of force between them is the amount of force that would be required to lift almost 100 kilograms and hold it up. Is that crazy? This is a lot of weight. What's that, 22 times 9? It's, yeah, it's 1,000 pounds of force. All these things together.
For clarification, so you said we're taking it from the opposite. We defined our coordinate system, and we're concerned with finding the force.
Now, to define your coordinate system, and especially with a simple charge,
Right.
You center your origin at not the charge you're looking at, but the charge that's interacting with it.
Okay.
It's a little bit backwards. Normally, we would sort of like to take whatever it is we're looking at and call it.
So if we define the coordinate system at Q2, would it be negative for R squared? Or it would be positive anyway?
Well,
B
it
squared.
depends on how you flip it around.
Right.
If we called this our coordinate system, now there's two ways to think about it, so there's just a little technical note. If we define this our coordinate system in a typical Cartesian way, our answer would be negative.
Right.
Because for the orientation being the same. Well, coordinate systems are, they're mushy. We can kind of do what we want with them. We could take this thing and twist it over and call this the positive direction, in which case this is the equivalent of this.
Right.
So, yeah.
Okay.
The three-line diagram has the force vector going to the left. Is that? I seem to be
Oh,
getting
no, I was
confused with
actually
that.
thinking the next problem that it's,
Oh, okay.
Okay, yeah, that makes sense, huh?
in fact, I think I even said that in words. I just pointed, I was just writing
Okay.
this example down here.
Okay.
So, thank you. That cleared me up.
So, very clear that they're repelling each other very strongly, so.
We are repelling each other extremely strongly.
So let's find the force that's holding it in the nucleus.
Well, that's actually pretty easy to figure out if these are the only two things there, right? If this thing is in equilibrium, then the net force has to be equal to 0.
Right.
If the net force is equal to 0, then whatever this force here, which must be particularly strong, have to be pointing in the opposite direction. So the
I just
interaction.
wanna know what it is.
This is called the strong force. Or it's related to the strong interaction. What produces it? Well, it's a Quarkian behavior, if you will. And it's the interaction that happens between what we call hadrons, which is a broader way of saying the nucleus. So both protons as well as neutrons have this attractive, strong interaction. Now, so if I had an extra nuclear or an extra neutron in here, that would change the game altogether, because I would have now more positive interactions with these other things as well, which would affect the spacing if everything still balances out to this electric force. So the problem becomes more dynamic when you put more players in the game, so to speak, but the same basic premise applies. This thing is going to be stable and held stable. Each of the things involved has to be equilibrium independent. So, try to pick the simple example and nothing else. So this is sort of the key. Now, if you had chemistry, what do we call, when you put neutrons, it's sort of a little aside, but everything is related. If you take a nucleus, and you got two protons, typically we say we add neutrons to the nucleus. Sometimes that will help stabilize the nucleus. What do we say? What do we normally refer to or think about when we talk about adding neutrons? What is it the neutrons act as when they're in the nucleus? Let me say they kind of act as a glue that holds things together. The interaction, the strong interaction, is actually mediated by what we call gluons. And a gluon is a strong analogy to how electrical forces are mediated, and electrical forces are mediated in what we call photons. Now we know that from light. At the time we didn't, but the interaction between electric charges happens via photons. And those photons, akin to light, is how that information between them is communicated. We talk about gravity, we call them gravitons. One of the big searches right now is trying to actually physically measure a gravity wave. Now, if we do that, we can start identifying how it quantizes, and its relationship to gravitons, and how gravitons relate to masses interacting over large spans in space. So, every time you have a force, you have a corresponding, well, we'll talk about field at some point. Gravity has a field, electrical forces, electrical charge have a field, strong forces have a field. And mediation of interaction between various entities at the same time are specific to the force interaction that generates them. In any case, that's sort of what's going on, but we won't worry so much about that at this point. But certainly the implication, if we got tons of force pushing these things apart, there has to be something that's pretty significant that's pulling them back together. And by the way, this unto itself would not be stable, because you would have to have additional entities in here that would help attract and pull together, because one nucleon does not generate enough strong force with another to counteract their electric force interaction, unless they're really close together, but not at the span that we normally see them occupy.
So what would be that force in that brings them together?
That would be the strong
That
force.
would be the strong force.
So, and the other reason why it's called strong, even though in this case we'd say it was the same value as the electric force, it's also called a strong force because it acts over much shorter distances than the electric force does. So you take two protons and stick them a certain distance away, their force of repulsion will be much greater than their force of attraction. It isn't until they get close enough that the force of attraction, due to this strong force, can lock them in together. So the strong force is orders of magnitude, apples to apples, larger in a very close proximity to the electric force as you get closer and closer, in the same sort of way that the electric force is so much stronger as you get closer and closer between objects to gravitational force. We've got all these layers of the onion that we don't necessarily want to concern ourselves too much with, but it's all sort of implied. All of this is just built into this simple model. Okay, so we have this number. Let's compare the gravitational interaction between these. Yeah, I mentioned last time very glibly, we just ignore gravity. And let's assume that gravity is relevant. Well, I just got done telling you there's a strong force of interaction, but this has mass, this has mass. For now, let's add the gravitational force too. I guess we can keep that strong force in there, or whatever the mystery force is involved. But I don't want to do a Newtonian equilibrium, set them equal to each other. I just want to calculate the gravitational force. Now, this was something that, at least with my class, because as we cut our loss, we just didn't spend any time on. But so the easy way, if you're near the surface of the Earth, it's m times g. But if you're at distances that are not approximately the distance between the center of the Earth to the surface, then the relationship is a little bit more intricate, but it looks very similar to electric force. So, for the next question, what is the gravitational force between them? I don't want to move around my business. Now, the way you calculate it for gravitational force, the interaction that generates gravitational attraction is mass. So we're no longer talking charge, now we talk mass. But the relation looks strikingly similar. The gravitational force between these two players is equal to the product of their individual masses and inversely related to the square of their distance of separation. And we have to apply another fudge factor constant. This constant is referred to as Newton's gravitational constant or universal gravitation constant. And you got to put a minus sign in here because it's always attractive. And as we defined our direction, the direction is outward in this coordinate system. But if it's an attractive force, it's going to be pulling inward. So the actual force in terms of the x direction is going to be negative in value, kind of like gravity pulls things down, negative mg. So this would be how we would calculate it. And g, this gravitation constant, is about 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Again, it's another engineering factor. Now note, just apples to apples on the surface, forget about the magnitudes of the interacting quantities, charge and mass. The distinction between the fudge factor for gravity and the fudge factor for electric force interaction are 20 orders of magnitude. So right there, that kind of tells you something significant. These interactions, all of them being equal, are mediated by constants that are way off the chart with respect to each other. And in sort of modern physical research, that's problematic, because these things are not closer to each other than we would expect. So we come up with all kinds of ways to explain why gravity's so small. Add more dimensions, just say it's all spread out in this direction. This is only one component of a bigger interaction that we just don't see. Okay, so we plug all of these values in, and we get minus 6.67 times 10 to the negative 11th meters squared per kilogram squared. And since they are of the same mass in this case, we can use 1.67 times 10 to the negative 27 kilograms squared. And we'll divide that. I don't know why I give myself so much space there. We'll divide this by, again, the same 5 times 10 to the negative 16 meters squared. So, on the surface, if we look at this, we might just say, okay, there's negative 38. And then we add to that 32, so let's see, that would be negative 8. Whatever this number is, it's going to be something on the order of negative 8 newtons. You give me a number.
Negative 7.44.
What's 7.44?
However, I've got
Negative 34.
times 10 to the negative 34.
Yeah.
Oh, I forget 27 squared. Oh, yeah. Okay, that makes a lot of sense. Okay, so negative 7.22, if you will, times 10 to the, well, 27 squared. There's 40, 54, 65 minus 16, so about 53, negative 54 in that ballpark. Did you say 53 or 54?
Negative
34.
Oh, 54? Oh, you subtract that. Okay, so newtons. That's FG. So the difference between the electric force and gravitational forces for this particular scenario is what, about 10 to the negative 36, or 36 orders of magnitude. Is that reasonable to say that when you're looking at charge interactions, we can pretty much neglect gravity on a microscopic scale? Is that reasonable? I'm not trying to shortchange or, like throw out air resistance. Kind of see how there's a huge, huge disparity. And I don't know why I'm doing that. I'm confusing you guys with my algebra-based class here. So, same mechanism, but we use x's instead of i's and y's instead of j's for the unit vector. Now, to this end, just if you wanted to just do a quick simplification, so we can compare these. If we looked at the ratio of FE to FG, and there's no reason to look any farther than just at their magnitudes. It's about 923 divided by 7.22 times 10 to the negative 34, which is, again, 34, 35, 36. So it's about 10 to the 36th power, give or take, 1.3 or something. Kind of give you some perspective to all of it. So, any questions how this works out?
Wait, I kind of missed out. What's FE over FG mean again?
I'm just looking at the relationship between the two. How do they compare? Let me add another.
Oh,
discussion.
okay.
Just sort of making some anecdotes here. So whenever you want to compare things, usually the best way to do it is by ratio. Because differences don't tell you the whole story unless you know how those differences are related to the size of the values.
Okay.
So how do basically FE and FG compare? And that's how we would calculate. And real quickly, let's also note that the ratio of FE to FG can be simplified because the ratios both have an inverse square separation distance relationship. That this ratio actually simplifies to this. So you don't even have to use the r's per se. The relationship will always be proportional, if they're the only two things involved, to this quick and very little expression. Is this divided by that, r's go away. Okay, so now let's just step out and look a little more. Now let's look at the atom. See what happens when we have a broader picture. See what these numbers look like. So if this is example number 1, let's look at example number 2. We call this number 1. Now, I'm gonna look at number 2. Let's look at 2 opposite charges. In this case, a proton and a negative charge electron. And let's change their separation distance. From 5 times 10 to the negative 16th to 5 times 10 to the negative 11. Half an atomic diameter. So now we have really the nucleus. And we have the electron that is sitting outside of this nucleus. Now there's a subtle difference here. Clean up some of these things now. So for the positive charge, the proton, its value is 6.02 times 10 to the negative 19th coulombs. But Q2 has a value of negative 1.602 times 10 to the negative 19th coulombs. And the mass, well, the mass of the proton is still 1.67 times 10 to the negative 27th kilograms. But the mass, let me change colors here for contrast, for this electron is about 9.11 times 10 to the negative 31 kilograms. So that's sort of an interesting point of observation. Protons and electrons have same but opposite charges, but electrons are like 1,000th the mass of a proton, which is why all the mass of an atom is locked into the center of this nucleus, 10 to the negative 15th dimensions, whereas the volume that we typically assign to how an electron occupies, or the atom is occupied, is like on the order of 10 to, well, dimensions of diameters on the order of about 10 to the 10, negative 10, not negative 15. So you've already got a detachment or dissociation between volume and mass. We're usually used to kind of thinking about homogeneous systems where the mass is uniform and consistent throughout, but that's absolutely not the case when you look at atomic scale. Okay, so I'm going to get rid of the free body diagram and look at these things. So let's start by looking at what the electric force is exerted on